Hello everyone, thank you all for coming. My name is Raoul Khouri, and today I'm going to be talking about some reinforcement learning experiments my team has been doing and how we migrated our technology stack to RLlib and Ray, and how that gave us a 24x speedup. So I'm an AI researcher at 2 Sigma, focusing primarily on reinforcement learning. Before this, I did my master's in undergrad at MIT in AI and computer science, respectively. And this is my dog, Bowie the Samoyed, his Instagram handle. So I work at 2 Sigma. For those of you who don't know, 2 Sigma is a financial sciences company. That means we focus on investment management as well as other financial data-driven endeavors. This includes insurance, real estate, private equity, client solutions, and a handful of other things. And the company was founded in 2001 by our co-chairman John Overdeck and David Siegel. And today we have about 2,000 employees, 1,000 engineers, 250 researchers, and 750 everything else. And we have offices in New York City, London, Houston, Tokyo, and Shanghai. This is our New York office, and I've recently voluntarily been going back to the office, which has been very nice. Since we are a financial sciences company, I do have to show this important legal disclaimer, then we can move on. So what are we going to talk about today? Well, my team has been doing a lot of applied research in reinforcement learning, and we recently migrated from stable baselines to RLlib and Ray. For those of you who don't know what stable baselines is, it's an open source reinforcement learning library that's built on top of baselines, which is another open source reinforcement learning library that was published by OpenAI. And then RLlib is an open source reinforcement learning library built in the Ray ecosystem, where Ray is this distributed compute ecosystem primarily in Python. And so we're going to talk about that migration, the speedups we got in that migration, and some lessons learned from that migration. And then we're also going to talk about our experiments and kind of a case study of our experiments and why we got such a speedup in our case in particular. So before we go into that, let's talk about a high-level overview of the reinforcement learning pipeline. So in general, you have what's called a trainer or an agent, and it's responsible for learning, right? And then you have this environment or simulator, and the trainer, gives out actions, and the environment simulator returns observations and rewards. So this environment's a state machine, actions go in, observations, rewards come out, and this trainer basically it wants to learn the set of actions, given observations, such that it can maximize the rewards to come out of the simulator. And so you can imagine that this might take a lot of interactions, sometimes millions, tens of millions, or hundreds of millions to get a good policy to come out of that trainer. And that could be a bottleneck. If the simulator is kind of slow, collecting 100 million samples can take a long time. So let's talk about our experiments. So, since we're a financial sciences company, we don't deal with the classic reinforcement learning, problems like cartpool or, robots or Mujuko or, walkers. We actually deal with financial data in time series. So there is a lot of financial data, so we have lots of data to deal with. And then there's also low signal to noise ratio, meaning that there's a lot of noise in financial data, and it can be very difficult to figure out some truth in it. And so because of this, getting stable results in our experiments was taking a very long time. We were finding it taking about 7 to 10 hours to complete. And at the time, we were using 24 CPUs with stable baselines. And so, we wanted to try to make our experiments a little bit faster. 7 to 10 hours, while acceptable, if it's, you only needed to do one experiment, we were trying to iterate, define the problem, iterate, kind of, experiment and do a good experimental cycle. And 7 to 10 hours basically meant we could do experiment maybe once a day. If something went wrong, it would take up a few days. We'd have to fix it, and it was very difficult to iterate and get good, stable results. And we found that learning was taking, less than 10% of our total time, and 90% of our time was spent sampling. So we were like, we can speed this up. We're good engineers. Let's try it. And so what did we try? Well, the first thing we tried, we're deep learning AI researchers. We were like, let's just throw GPUs at this. We have some GPUs machines. Let's try it. But we found that quickly it yielded little to no speed up. So, simulators don't use GPUs. RL is, or at least our case, we were simulator bound. So GPUs weren't really going to help. We didn't own the simulator, so we couldn't just write it such that GPUs would speed it up. So this wasn't going to help us. And GPUs are pretty expensive. Those GPU machines are not cheap. So this wasn't really a good option. It might have sped up our inference, but really not worth it. And I remember at a conference, I think a year ago, Someone was saying, I got a machine with a larger GPU, but I'm not seeing a speed up in my RL library. What's wrong? Why is this broken? And it's unfortunately a lot of times your simulator bound GPUs aren't going to help. So the next thing we tried was throwing more CPUs at the problem. So we tried machines with more than 24 CPUs on stable baselines, and we found that actually we didn't get a speed up. And this was the thing that really shocked us. We were getting a certain sampling per second at 24 CPUs. We imagined if we doubled the number of samplers we have to 48 CPUs, collecting twice as many samples per second, we should collect twice as many samples per second. But we found that going from 24 to 48 or more CPUs, we found almost no speed up. And this was kind of shocking. We couldn't really explain what was wrong here. And so at that time, there was this other reinforcement learning library called RLlib that my team had on its radar. And I was like, okay, let me try this other library out and see maybe if we get a speed up. So I migrated to RLlib, right? Thankfully, our simulator was already in the generic GIM API, so the environment migration was pretty easy. And RLlib has a superset of the algorithms versus stable baseline, so we didn't really have to make any consolations during the migration. So it was a small change in hyperparameters, and eventually, within a week, we were able to get the same solution quality. And so that was all great, and there was great community support and everything. And so we got same solution quality, but going back to the original question, did this make it faster? Was RLlib faster? So we then did this kind of shootout where we compared the RLlib simulator or RLlib experiments to the baselines experiments, and we varied the number of CPUs we provided to each of them. And we saw that RLlib, as you can see in this plot, RLlib was much faster when you started giving it more CPUs. It parallelized a lot better. In fact, we found that at 24 CPUs, RLlib was about 4 times faster than stable baselines. And this was kind of shocking because they're using, it's fundamentally the same idea. It's the same algorithm in many ways, and you're using the same amount of compute. So why was RLlib faster? And I think it comes down to basically the types of parallelization that an RLlib library can do. So the first type of parallelization you can do is called a vectorized environment, right? So you can take all your environments and you basically put them into what's called a vector, right? And then you basically step them all together. So you tell them all to step, you wait for them to step forward, and then you get the observations, and then you take all those observations and you push it through your deep learning library. Together, you get actions out of all your policies, and then you push it back through the environment. And this is actually pretty efficient in inference time because everything's in a vector. You can kind of do a bunch of vectorized stuff. However, if one of your environments is slow, all your environments are slow because they have to step together, right? So it can be very inefficient if you have kind of big variance in the time it takes each environment to step. We call this the lockstep issue. So one environment's kind of locking your entire vector, and you're actually constrained to this by many RL libraries, and it's not very public what they're doing. And so, for example, this might be what a vectorized environment looks like. You have 5 environments inside of it, and when you asked to step, one of the environments was kind of slow. In this case, 100 milliseconds rather than 3 milliseconds like all the other environments. And that caused basically the entire vector of environments to all take 100 milliseconds. And you can imagine that there's a lot of wasted compute here. The other option here, the other alternative, is called a batch rollout. And basically what you do is you would take all those 5 environments and say, hey, why don't you guys all collect 10,000 samples and come back to me when you're done collecting 10,000 samples. It might be a little less efficient in inference time because each of those environments are going to have to interact with the TensorFlow graph separately, so you can't do it kind of a vectorized TensorFlow operation. However, since they sync at the end of the rollout, you're less concerned about one locking up just for one step and slowing everyone down. You kind of distribute the risk of those slowdowns. As long as it's not a systematic slowdown, it's just like one step might be slower because it has to do more compute or something. So on average, this requires a lot less waiting. You basically avoid the lockstep issue. So you can imagine in the simulator where you have 5 environments and one of them on average is going to take 100 milliseconds. Over a long period of time, this kind of setup would only take about 23 milliseconds per step, which is a lot better than the 100 milliseconds with the vectorized setup here, configuration here. And so the lockstep issue is actually what was causing our stable baselines experiments to not parallelize well. So what's the RLlib solution to parallelization? It's actually a hybrid solution. So it's interesting, you actually get to choose kind of the number of batch rollouts you want to do, and then within those batch rollouts, you basically get to pick the size of the vectors, right? So you can imagine it being very customizable. So you can see here one configuration where you have basically 4 batches. Within each batch, you have 3 vectors, so you still have 24 environments. But here, you have another configuration with 6 batches, each with 2 environments in them, still 24 environments, but you can see that the average step time in the second configuration is a lot faster. And that's just because you're kind of distributing those slowdowns better. So going back to our experiment, if we kind of diagnose the runtimes and all the kind of sampling procedures, our overall performance, between RLlib and stable baselines for the optimization was identical. But for sampling, we were seeing that RLlib was basically 7 to 8 times faster than stable baselines. And if we kind of break down sampling, we see that they took roughly about the same amount of time to reset. And in fact, stable baselines was slightly faster at inference. And we talked about why. But interestingly enough, when we actually came to stepping through our environment, we found that RLlib was a lot faster, 21 milliseconds faster per step. It might not seem like a lot, but when we're collecting 20 million samples, be it across 20 CPUs, that ended up being about 6 hours wasted of just CPUs sitting there over our experiments, which is just a lot of wasted possible compute. And so, we had these environments, and you can imagine a lot of CPUs were just not computing in periods of time, which was not great. And so one of the really nice things, though, on top of RLlib and the way it parallelizes, is that RLlib is also part of the Ray ecosystem. And being part of the Ray ecosystem opens the door to basically taking advantage of the distributed compute that Ray provides through Ray clusters and the entire Ray library. And so we originally showed this graph, and by using RLlib in conjunction with Ray, we open up the right side of this graph, access to additional machines, being able to easily take our experiments beyond just 24 CPUs and go all the way out to 380 and possibly beyond, but we didn't for this experiment. And this was pretty great. So we got our experiments all the way down to basically just taking about 20 minutes, be it using 380 CPUs, almost 16x the CPUs, but down to 20 minutes. And so that meant our research cycles were much faster. We were able to run a couple experiments in the morning, get results, look at them, keep running experiments throughout the day, and completely revolutionized kind of our experiment cycles and the way we were kind of being able to iterate. It's really helped us. And we were using about 16x the CPUs and saw about 6x speed up from doing so. So being part of this Ray, being in this Ray ecosystem was great. So in conclusion, we migrated from stable baselines to RLlib. I think mileage is going to vary here depending on the experiment and what you're doing. We saw 4x speed up. I think what people should be aware of is how their RL library is parallelizing, and whether or not their experiment is going to be susceptible to the lockstep issue. And if it is, be very aware of what you're using, possibly to consider using RLlib. And then also think about how you could distribute your simulator across multiple computers. Whether you want to use Ray, which allows you, I think pretty easily do this and works really nicely with RLlib. You can, scale really well. I think mileage is going to vary here. We saw a nice 6x speed up. I think you can see this as well. And it's pretty easy since it only required commodity CPU only machines, which are relatively cheap and easy to get nowadays. So together we saw about a 24x speed up, 4x and 6x, which brought our experiments from 7 to 10 hours down to 20 minutes, which was great. Completely different research cycles. So I hope this helps you guys speed up your experiment and get better results. Thank you very much.